Hello, welcome to a new lesson in differential equations. Today we are going to look to a new example of how to find the green function for a particular differential equation given its boundary conditions. So today's problem is x y double prime of x plus y prime of x minus 4 divided by x times y is equal to f of x, where remember that this f of x, that is the non-homogeneous term, well, it is an arbitrary function, right? In this case, the conditions that define this problem is that x is going to be bigger than or equal to 1, and that y evaluated at 1 is equal to 0. Okay, so how are we going to proceed? Well, we know that the first step is to find what is the associated differential equation for the green function of this problem, right? So it is easy to find. We have seen in recent lessons that we can find that differential equation as the next form. It will be x, the second derivative of the green function, plus the green function in its first derivative, right? Then minus 4 divided by x, the green function, and this is equal to the Dirac delta. Okay, notice that we just need to substitute the y's for the green function, take the same order derivatives, and well, instead of writing f of x, well, we just write the Dirac delta. Okay, perfect. So this is the associated green function differential equation that we are going to use to solve this problem. And you also know that, well, to be able to make a proposal of the form of the green function, we first need to solve the homogeneous version of the differential equation, right? So from this solution, we are able to construct the first proposal of the green function. So we need to find the solution to the next differential equation. It will be x y double prime plus y prime minus 4 divided by x times y equals to f of, well, actually 0, right? Because remember that we said that we need to find the solution to the homogeneous version of this equation over here. Okay, so we easily identify that this is an Euler differential equation, right? A type of equation which is known as Euler equation. So you know that Euler equations from your basic course in differential equations can be solved if you propose a solution of the form y of x equals x to the m. We need to find what is m, and then the solution will be a linear combination of functions of this type. Okay, so what happens if we take the first derivative? Well, we are going to get that this is m times x to the m minus 1, and then the second derivative is m times m minus 1 times x to the m minus 2. So we need to substitute this into the differential equation, of course. So we will get that x times m minus 1 times x to the m minus 2 plus y prime, which is m x to the m minus 1 minus 4 divided by x times x to the m is equal to 0. So from here, we get that m times m minus 1 x to the m minus 1 plus m times x to the m minus 1 minus 4 x to the m minus 1 is equal to 0. Then we can cancel the factor x to the m minus 1 to get that m times m minus 1 plus m minus 4 is equal to 0. From here, we get that m squared minus m plus m minus 4 is equal to 0. So we easily get that m should be equal to plus or minus 2. Okay, so this means that y1, let's say, it is equal to x squared, and y2 should be equal to x to the minus 2, right? So from here, we can construct a solution of the form, let's say, well, a1 to the times x squared, and then plus a2 x to the negative 2. Okay, so with this function that we have here, we have a motivation to construct the green function. Recall that in this case, these are only constants, okay? These are just numbers. But looking that the green function is a function of two variables, well, the constants that are going to be next to the x, well, are not going to be constants, are actually going to be functions of x prime, which is the other variable of the green function. This one over here, right? So, yeah, we are going to propose a green function of the next form. It will be something like this. A of x prime times x squared plus b of x prime x to the negative 2, like this. And then second piece for the green function will be c of x prime x squared plus d of x prime x to the negative 2. Recall that I'm splitting into two pieces the green function because we know that at the point x prime, the derivative of the green function is not continuous. So we know that it is convenient to split into two pieces the green function due to this reason. But we know also that the green function should be continuous at x prime, right? Okay, so actually those are the conditions that we are going to use to finally find out what are these functions a, b, c, and d, which is actually the objective of this lesson. So from here, we are going to say that this definition will be applying for 1, which is less than or equal to x, which is less than x prime, and the other one, x bigger than x prime, which is of course bigger than or equal to 1. Okay, so we split the green function into two pieces from the left of x prime and from the right of x prime. Okay, perfect. Okay, so as we did in the previous lesson, where we also find the green function of a particular differential equation, we need to use the boundary conditions to reduce the number of equations that we have to find a, b, c, and d. And then we will use the properties of the green function to find other two equations that will help us to find finally a, b, c, and d. Okay, so we are going to make use of the first boundary condition that tells us that the green function evaluated at x equals 1 is equal to 0. Recall that this comes from this condition that tells us that y evaluated at x equals 1 is equal to 0. Recall that if y satisfies the boundary condition, then it is necessary to for the green function to satisfy the same exactly condition, because we see here from this equation that the green function also satisfies the structure of the differential equation. So that means that, well, the green function evaluated at x equals 1 should be equal to 0, right? Okay, so looking that x is equal to 1, we are in the first region, right? So we need to use this definition. So this is going to tell us that a of x prime evaluated at 1 plus b of x prime evaluated at 1 to the negative 2, well, it should be equal to 0. And this tells us immediately that a of x prime is equal to negative b of x prime. So this is our first important equation. Okay, so now we are going to make use of another condition that defines the problem that I didn't mention at the beginning, but it is important to mention right now. We see here that, well, we have two functions of x, right, that are, well, in this case, we have the x squared, which is the important one. We see that in particular, x does not have any limit, right? It goes to infinity. For watching just this interval, we see that x has no limit in principle. But we would like the green function to converge. I mean that we do not want to go to the infinity, right? So that means that we would like to have this element to be equal to 0, because if not, then the green function does not converge. Okay, so the condition of convergence tells us immediately that a c of x prime is necessarily equal to 0. Okay, perfect. So with this, we can say that the green function can be defined as a of x prime, x squared, and then b, but b is equal to minus a, right? So we will have here minus a of x prime, x to the negative 2, and then we will have a d of x prime, x to the negative 2. Okay, perfect. Just to simplify, let me write this as a of x prime times x squared minus x to the negative 2, and then d of x prime times x to the negative 2. Obviously, these are defined in the same intervals that I wrote here, but for simplicity, I'm not going to write them all the time. Okay, so for now, we have this for the green function. So what is next? So what can we do to find the value of a and d? Well, we know that at x prime, g is continuous. So that means that these two pieces should be equal when x is equal to x prime. So from that, we can construct quickly another equation that is a of x prime times x prime squared minus x prime to the negative 2 should be equal to d of x prime times x prime to the negative 2. But that is equivalent to say that minus d of x prime times x prime to the negative 2 is equal to 0. So this is the continuity condition for the green function, just to say it in a different way. Okay, and as we did on the previous lesson, we are going to construct a system of equations. So this will be like the first equation of that system. And then recall that what we do to construct the second equation is to take this equation again, we integrate on a convenient interval, and then we find some expression for the derivatives of the green function, right? So let's do it again, just to show you how it's done. And let me copy this into another page. Okay, so we have here the differential equation for the green function. So what we do that results more convenient is to integrate on a neighborhood of x prime, you know. So if we do that, we are going to get the next. It will be the integral from x prime minus epsilon to x prime plus epsilon of x g double prime of x comma x prime plus g prime of x comma x prime dx, and then minus, let's say, 4 times the integral from x prime minus epsilon to x prime plus epsilon of g of x comma x prime divided by x, and this is equal to the integral from x prime minus epsilon to x prime plus epsilon of the Dirac delta dx. Okay, as we have been saying in recent lessons, we know that this integral should be equal to 1, because x prime belongs to the interval of integration. And we know that when the variable of the Dirac delta is inside the interval of the integral, well, that integral is equal to 1, right? From here, we know that looking that the green function is continuous at x prime, if we take the limit as epsilon goes to 0, well, we will get an integral from x prime to x prime. But, well, we know that every integral of that type of a well-behaved function, like g in this case, well, it's going to be equal to 0, right? If epsilon goes to 0. So this whole element disappears. And from here, it's easy to see that this piece can be seen as the derivative with respect to x, or in this case, let's say actually the partial derivative with respect to x, right? Because g, well, is a function of two variables, of g prime times x. Okay? And noticing that this integral is of the variable x and this derivative is of the variable x, we know that we can cancel the derivative with the integral. So we will get the next x times g prime of x comma x prime evaluated from x prime minus epsilon to x prime plus epsilon is equal to 1. Okay? Perfect. So recall that this is the derivative of the green function. So as epsilon goes to 0, it's just like taking the left derivative and the right derivative, right? So we need to evaluate x at x prime from the right in this case, and then from the left. Okay. So this will be equivalent to say that x prime multiplies the derivative of g evaluated at x prime from the right, like this, and then minus the derivative of g evaluated at x prime from the left of x prime here. The derivative is with respect to x, and then this is equal to 1. Okay. And well, it is important to make this difference because the derivatives in this case are not equal. Looking that we define the green function to be different from the right of x prime and from the left of x prime. Recall that this definition is for x less than x prime, and this one is for x bigger than x prime. Okay, so when we calculate the derivative, we need to take this difference into consideration. So in this case, for example, we are going to take the derivative with respect to x of g from the right. So we need to take the derivative of this function over here and then evaluate at x prime, right? So what will we get if we do that? So, well, first of all, let me take this x prime to divide here. So we are going to get the next d of x prime and then minus 2x to the negative 3. Okay. And then minus the derivative with respect to x of g, but from the left, right? So in this case, we need to take this expression for g and evaluate it at x prime. Okay, so it will be minus a of x prime 2 times x. Let me evaluate at the end, right? Okay, so then it will be plus a of x prime minus 2 x to the minus 3. Yep, and then all these evaluated at x equals x prime. And this is 1 divided by x prime. Okay, so we get the next minus d of x prime. Let me write this 2 here. X prime to the minus 3 minus 2 x prime a of x prime minus 2 a of x prime to the minus 3 equal to 1 divided by x prime. And I think that it was better not to take this x prime to the denominator in the right hand side of the equation, right? Because, well, we can cancel some terms if we take this again to the left hand side. So this equation is equivalent to minus 2d of x prime to the minus 2 x prime squared a of x prime minus 2 a of x prime x to the negative 2, and this is equal to 1. Okay, so if we join together the elements that are common for a of x prime, we are going to get the next equation. A of x prime times minus 2x prime squared minus 2x, and this is prime, right? X prime to the negative 2, and then minus d of x prime 2x prime to the negative 2 equals to 1. Okay, so with this, we have the second equation that we needed to find the green function. Okay, perfect. So Well, I'm actually going to rewrite this equation in a prettier way. It will be a of x prime, let's say 2 times x prime squared plus x prime to the negative 2 plus d of x prime 2 times x prime to the negative 2 equals minus 1, right? Just by multiplying by minus 1 on both sides of the equation. Okay, and let me bring back the other equation that we found, which was a of x prime times x prime squared minus x prime to the negative 2 minus d of x prime to the negative 2 equals to 0. Okay, so this is the system of equations that we need to solve. Again, we are going to make use of the Cramer rule to solve it. So a of x prime is equal to, what is this going to be? Well, we will have here minus 1, and then 0 here, and then 2x prime to the negative 2 here, and minus x prime to the negative 2. Okay, and this is divided by, it will be 2 times x prime squared plus x prime to the negative 2. Then here it will be x prime squared minus x prime to the negative 2. Here it will be 2x prime to the negative 2, and then minus x prime to the negative 2. Okay, so what are we going to get? It will be x prime to the negative 2 here at the numerator, divided by, here we are going to get minus 2. So it will be this times this is equal to 1, and then minus 2 x prime to the negative 4. Okay, and then we will have minus 2. Again, this times this is equal to 1, and this times this will be plus 2 times x prime to the negative 4, which is going to cancel with this element. Perfect. So from here we get that a of x prime is equal to x prime to the negative 2 divided by minus 4. So this tells us that a of x prime is equal to 1 or minus 1 divided by 4 x prime squared. Okay, perfect. So that's our first important result. So what is going to be b of x prime? Well, we have that b of x prime should be equal to, well, here we have 2x prime squared plus x prime to the negative 2. Here we have x prime squared minus x prime to the negative 2, and then a minus 1, 0 here, and then all divided by, well, the same denominator that we have here, but we see that it is a minus 4, right? So all these things is going to be minus 4. So from here we get that we have x prime squared minus x prime to the negative 2, and then divided by minus 4 like this. Yeah. Okay. And actually, this is not b, right? This is d of x prime. Okay, so let me bring back the definition of the green function just to complete the result. Okay, so this is what we set for the definition of the green function. So this, if we take the results that we just found, well, we are going to get that. Here we have minus x prime to the negative 2 divided by 4 multiplies x squared minus x to the negative 2. And for this piece, we have that x to the negative 2 multiplies x prime squared minus x prime to the negative 2, all divided by minus 4. Okay, perfect. Let's recall again that this is for 1 less than or equal to x and less than x prime. And then we will have 1 less than or equal to x prime less than x. Okay, so this will be the green function of the differential equation shown at the beginning of the lesson. Perfect. So I think that with this, I'm going to finish the lesson. And thank you so much for watching.